Hello guys, we're back in chapter 15, and what we're getting ready to talk about right now is important in that we're going to learn the basics of solving equilibrium chemistry problems here in chapter 15. We're going to do the same thing in chapter 16 and the same thing in chapter 17. So it's critical that you understand what we're doing in this part of the chapter to be able to succeed in the next two chapters. Okay? Now, when we talk about solving equilibrium problems, there are different types of equilibrium problems. The first type is given an equilibrium constant and finding an equilibrium constant given all concentrations at equilibrium. That's a bunny hop problem. Okay? We want to find the equilibrium constant given all initial concentrations and one concentration at equilibrium. Now that's a more atypical way to calculate an equilibrium constant, because if we're looking at monitoring concentrations in a chemical reaction, we usually can only monitor the concentration of one of the components over the course of the reaction. The third type is the most critical type for us to understand moving forward, and it's given an equilibrium constant and initial concentrations, find the concentrations at equilibrium. And we're going to look at three ways to solve this kind of problem: a perfect square, an assumption, and the dreaded quadratic. Okay? So we're going to step our way through this, and we're going to look at examples of each one of these problems. Okay, guys, let's see. Now, no matter what problem type we're looking at, we've always got to have a balanced chemical equation, and we've always got to write out the equilibrium expression based on that chemical equation. So no matter what you're doing problem solving, the first two things you do is write out the balanced chemical equation and then write out the K expression. Now, in our problem type 1, where we're given all concentrations at equilibrium and we write out the K expression and plug in all concentrations and solve for K, it's an easy problem. We're going to look at problem 36 on page 677 in your textbook. Okay? 677, that's at the end of the text. It's in the homework problem. And we're looking at problem 36. Now, scoot over here with me. And here we go. We look at problem 36. It says, consider the reaction NH4 HS solid going to NH3 gas plus H2S gas. Okay, now that's a balanced chemical equation: 1 nitrogen, 1 nitrogen, 1 sulfur, 1 sulfur, 4, 5 hydrogens, 3, 4, 5 hydrogens. Okay, now that means I can go ahead and write the equilibrium expression. K is going to be the concentration of ammonia times the concentration of hydrogen sulfide. And since hydrogen sulfide is a solid, there's nothing in the bottom. That's just the equilibrium expression. If that bothers you, you can put a 1 here on the bottom. Okay? Now, the other things we're told is that at equilibrium, the concentration of ammonia is 0.278 molar, and the concentration of H2S is 0.355 molar. Okay? So So all I have to do is take these equilibrium concentrations and plug them into the K expression. So I get 0.278 times 0.355. And again, I walked into this room without my calculator, so I'm going to have to use my phone. I apologize. Let's see, find a calculator. 0.278 times 0.355. And we get an answer of 0.09869. We only have 3 significant figures, so 0.0987. Okay, guys, it's always a good idea to box in your answer when you're done. So that's a real straightforward, simple problem. Okay, so let's move on to the next type of problem. Gear up just a little bit. Okay guys, here in problem type 2, find K given all initial concentrations and one concentration at equilibrium. You don't automatically know all of the concentrations at equilibrium. We've got to figure out some of the concentrations at equilibrium before we can solve for K. And to do this, we're going to use a tool called an ice chart. Okay, I stands for initial concentration, C stands for change in concentration, and E computer and I are fighting. E stands for equilibrium concentration. Okay, so scooch it over. Ice chart. Okay, ice chart is a chart that lists the initial concentrations of reactants and products, change in concentration of reactants and products, and equilibrium concentrations of reactants and products. So when we construct an ice chart, we're going to have 3 lines on the ice chart. One for the initial, one for the change, and one for the final. And we're going to choose a variable x to correspond to whichever reactant or product has a coefficient of 1. It makes our life easier. Okay, so let me show you what's going on here. Now, to show you how this works, we're going to look at problem 15.15 on page 653 in your textbook. 15.15 is one of those embedded problems. Okay? 653. Now, the problem reads, the reaction shown in 15.15 between carbon monoxide and hydrogen is carried out at a different temperature with initial concentrations of carbon monoxide of 0.27 molar and hydrogen at 0.49 molar. At equilibrium, the concentration of CH3OH is 0.11. Find the equilibrium constant at this temperature. Okay, let's build some stuff. All right, let's get the board clean here. Now, the reaction we're dealing with is carbon monoxide plus 2 hydrogens, both in the gas phase, going to CH3OH. Now, the first thing I want you to notice here, I want you to check is if it's balanced. 1 carbon, 1 carbon, 1 oxygen, 1 oxygen, 4 hydrogens, 4 hydrogens. It's balanced. That's the gas phase. Now I'm going to go ahead and write my equilibrium expression. Concentration of CH3OH, equilibrium, over the concentration of carbon monoxide at equilibrium, times the concentration of hydrogen squared at equilibrium. Okay? Now we're going to build an ice chart. Initial change equilibrium. And across the top, I'm just going to list my reactants and then my products. So carbon monoxide, hydrogen, CH3OH. Now, we're told that the initial concentration of our carbon monoxide is 0.27. Our initial concentration of hydrogen is 0.49. In the problem, it doesn't say anything about there being any CH3OH in there to begin with, so we know it's 0. Now, because there is no product in the beginning, I know that initially this reaction has to be running in the forward direction to get to equilibrium. So I know I'm going to have to eat up some carbon monoxide, and I'm going to have to eat up some hydrogen. So the change in carbon monoxide and hydrogen is going to have to be negative. Okay, the coefficient in front of carbon monoxide is 1. So I'm going to say minus x. Or you could say minus 1x. There's a coefficient of 2 in front of the hydrogen. For every 1 carbon monoxide that's lost, we're going to lose 2 hydrogens. So minus 2x there. And we make 1 CH3OH, which is methanol. So that's plus x. If I take the initial and the change line and I add them together, I get the equilibrium line. So 0.27 minus x, 0.49 minus 2x, and x. Now, the other piece of information we're told is that at equilibrium, the concentration of CH3OH, the methanol, is 0.11 molar. So we know that this guy is 0.11 molar. So that gave me x. So x is 0.11 molar. So 0.27 minus x is 0.16 molar. And 0.49 minus 2x would be 0.49 minus 2 times 0.11, which would be 0.22. 2 from 9 is 7, 2 from 4 is 2. So 0.27. So let me write those in, and we'll write them in pink. So this is 0.16 and this is 0.27. Okay? So now I have all the concentrations at equilibrium, and all I have to do is plug into the K expression. K then is 0.11 over 0.16 times 0.27 squared. So let's get an answer. 0.11 divided by 0.16 divided by 0.27 squared. So I get an answer here of 9.4. Now, I usually run my numbers twice because I never trust my calculator. It lies to me all the time. So I'm going to run it a second time just to check. I got the same answer, so I believe it. Okay? Now, the critical thing to pick up here is this ice chart. Ice chart is going to be important in every problem essentially we solve from here on out for the next 3 chapters. Okay, so ice charts are important. Okay, so let's drag this down a little bit. And let's talk about our third type of problem. Okay? The third type of problem is the problem that we're going to do most often. And in this problem, we're going to be finding concentrations at equilibrium given an initial concentration and the value of the equilibrium constant. Because when we're studying equilibrium chemistry, what we're interested in is how much product can I really get out of this reaction. Okay? So, we always do 4 things before we think about anything else. We balance the chemical equation, or check it for balance. We write the equilibrium expression. We create an ice chart. We transfer the values with the variable x from the equilibrium line of the ice chart into the equilibrium expression. And then we choose a solving procedure. Okay? So we're going to write a balanced chemical equation. We're going to write the equilibrium expression. We're going to create an ice chart. We're going to transfer those values with the variables into the equilibrium, from the equilibrium line into the ice chart, and then we're going to solve. All right, there are 3 ways to solve this problem based on what the algebraic equation looks like when we've plugged into K. Now, the easiest case is a perfect square. When we've plugged into the equilibrium expression where we've got the value of K, and notice I've got x times x on top and 0.20 minus x squared on the bottom. So I see I have x squared over 2 minus x squared. This is a perfect square. Okay? Now when we have a perfect square, the easiest way to solve this is step 1, take the square root of both sides. So the first thing that we're going to do is we're going to take the square root of both sides. Okay? When you get to this point, 10 equals x over 2 minus x, it's algebraically very easy to solve. So let me solve that on out for you. Okay? So if we think about this, if I have 10 equals x over 2 minus x, then I have 10 times 2 minus x is equal to x. So I have 20 minus 10x is equal to x, or 20 equals 11x. So x is going to be 20 divided by 11. Okay? It's an easy solve. If all of them were perfect squares, our lives would be perfect. Unfortunately, they're not. Okay? Case 2. In case 2, here, you don't have a perfect square. So the next thing we look to do, if it's not a perfect square, is determine if we can make assumptions. Assumptions are kind of fudge factors, but the numbers we're dealing with are sometimes x is so small that we can fudge. Okay? So if you don't have a perfect square, we're going to look to see if we can have an assumption. When we look to see if we can have an assumption, we're going to be looking at the value of K and the initial concentrations of our reactants. Okay? To make an assumption, the magnitude of K has to be at least 1,000 times smaller than your smallest or lowest starting concentrations. Then making an assumption should be possible. So what do I mean by that? Well, let's say that my concentration of one of my materials is 0.2. Then I want my K value to be less than 2 times 10 to the minus 4 to make an assumption. Okay? The smaller K is, the more likely we are to be able to make an assumption. What we're doing here is saying that X is going to be so small when we solve for it, that when I subtract it from that initial concentration, with significant figures, I'm probably not going to see a change in the value, okay? So you approximately get the initial value. As long as x, when you solve for it, is less than 5% of the lowest initial concentration, your assumption is valid. So let's look at an example here. Okay, the reason that we want to make assumptions is that when we make assumptions, it makes the math easier. So let's look at this example here. Okay, we've taken everything from the equilibrium line of our ice chart and we've plugged it into our K expression. And I've got 0.00052, that's the value of the equilibrium constant, equals x squared over 0.2 minus x times 0.3 minus x. Well, 0.2 is our smallest initial concentration. This guy is quite a bit smaller in the right range. So I am going to assume that 0.2 minus x is approximately 0.2, and that 0.3 minus x is approximately 0.3. So if I make that assumption, then I end up with 0.00052 is equal to x squared over 0.2 times 0.3, which is x squared over 0.06. Okay? So if I multiply through by the 0.06, I get 3.12 times 10 to the minus 5, and I don't know why that exponent came down, but let me fix that. Okay, that should be a superscript. So 3.12 times 10 to the minus 5 is equal to x squared, and x is equal to 5.6 times 10 to the minus 3. Now, we want to check our assumption. When we check our assumption, the magnitude of x has to be less than 5% of the initial concentration. So I take x divided by initial concentration times times 100%, and I want an answer less than 5. So 5.6 times 10 to the minus 3 divided by 0.2 times 100 gives me 2.8%. That means the assumption was valid. Okay? So it's a valid assumption. Chapter 16, when we get into acid-base chemistry, one of our main approaches to problem solving is the assumption. Okay? So you need to get good at it. Now, let's scroll on down. And let's look at our case 3. This is our worst case scenario unless you like doing the quadratic equation. Most people groan when I say we've got to do the quadratic equation. But in some situations, okay, we can't help it. If you didn't have a perfect square and you cannot make an assumption, then you're going to be stuck doing a quadratic. So consider this DEFCON 5. All right, so let's look at what we're going to get when I'm at DEFCON 5. So when I plug everything into the equilibrium expression, the value of K, and the things from my equilibrium line. Here, notice I've got x over 0.3 minus x squared. There's not a square top and bottom, so it's not a perfect square. And if I look at 0.3 and 0.556, my K value is larger than my initial concentration. There's absolutely no way that I can make an assumption. So the first thing we're going to have to do is we're going to have to FOIL this out. So I get 0.09 minus 0.6x plus x squared. We continue on with our algebra, and this is just algebra, guys. Nothing new or novel. Sorry. So if I continue on, I'm going to multiply through by the 0.09 minus 0.6 plus x squared. When I do that, I get 0.05 minus 0.33x plus 0.556x squared equals x. Get everything on one side. And remember, we're looking for ax squared plus bx plus c equals 0. Now, this is my squared term, so a is 0.556. Remember, looking for this form, ax squared plus bx plus c. B is minus 1.33, and my c is 0.05. If you want to rewrite that equation so you got it written in, ax squared plus bx plus c form equals 0, do it. Whatever makes the math work best for you. Then we've got to do the quadratic. X equals a negative b plus or minus b squared minus 4ac over 2a. So x is going to equal 1.33 plus or minus the square root of 1.33 squared minus 4 times 0.556 times 0.05 over 2 times 0.556. Now, when I do this, when you do the quadratic, you always get two solutions. Mathematically, both solutions are valid. Chemically, only one of the solutions is going to be valid. Okay? Now, the value 2.35 mathematically possible, but chemically is impossible. Because if I were to subtract that from the initial concentration of the reactant, which was 0.3, I get a negative value. And you can't have negative concentrations. So 2.35 mathematically is valid, chemically is invalid. Okay? So the correct answer here is 0.036. Now we're going to look at 3 problems. And as we look at these problems, what we're going to be trying to do is determine which way to solve the problem. Okay? So we're going to ask ourselves the questions. What kind of problem is it? Now these problems are all at the end of the chapter. They're on page 678. There are sample problems embedded in the text. Okay, so problem 15.12, 15.13 are examples of problems that you can solve here. 15.11, and because they're practice problems, they've got the solutions at the end of the chapter, so I'm not going to do those so that you can use them for practice. We're going to work some at the end of the chapter. So we're going to start with problem 54. Okay? Now let me slide you over here because we're doing problem solving again. Now, stay put. It says that for the reaction, carbon monoxide gas plus chlorine gas, we go to carbon monoxide dichloride gas. Okay? And it says the value of K is 255. And so I'm going to write my equilibrium expression here, which is concentration of carbon monoxide dichloride over the concentration of carbon monoxide times the concentration of chlorine. Okay? And I'm going to go ahead and draw my ice chart. Carbon monoxide, chlorine, carbon dioxide, dichloride. Now, we're told that the initial concentration of carbon monoxide is 0.15 0.00 molar. The initial concentration of chlorine is 0.175 molar, and there's no carbon monoxide dichloride at equilibrium. It says, what are the concentrations of everything at equilibrium? Well, I know this is going to be minus X, and this is going to be minus X, and this is going to be plus X. So at equilibrium, I have 0.1500 minus X, 0.1750 minus X, and X. So let's plug everything we know into the K expression. 255 is going to equal X over 0.1500 minus X times 0.1750 minus X. And now's when I stop and I look to decide how we're going to solve the problem. If I look at this, there's not a square term on top, so I know it's not a perfect square. The value of K is larger than my starting concentrations. So I can't make an assumption. This is DEFCON 5, this is going to be a quadratic. So let's start foiling this out. So 255 is going to equal X over 0.1500 times 0.1750, and I get 0.02625 minus 0.150, clear, 0.150 plus 0.175, so 0.325x plus x squared. Okay, so then we're going to go 255 times 0.02625 minus 0.325x plus x squared equals x. So clear that out. 0.02625 times 255 equals, so I have 6.69375, I'm going to worry about significant figures at the end, minus 255 times 0.325, 82.875x plus 255x squared equals x. Now guys, I'm running out of board room that I know you can see, so I'm going to erase a little bit here to give me a little working room because I don't, well, wait a minute. Let's see if I can't do this. Let's see if I can slide us over a little and get some board space here. Turn this down just a little bit. All right, guys, I can keep rolling. Now, what that means is I've got 255x squared minus 82.875x plus 6.69375 equals 0. So x is going to equal a negative 82.875 plus or minus the square root of 82.875 squared minus 4 times 255 times 6.69375 all over 2 times 255. Okay, so I'm going to get two solutions here. Give ourselves a little room here to work. So, let's see if I can do this on my phone. So, clear everything out. And I have 82.875, and I need to square that. Well, that doesn't have a square on it. Times 82.875, okay. And I'm going to subtract 4 times 255 times 6.69375 in parentheses. It equals, and then I want to take the square root of that. Okay, square root equals. So I've got x equals 82.875 plus or minus 6.37 over 2 times 255. Okay, clear. So 82.875. Let's add 6.37 and divide by 2 and divide by 255. So one answer I get is 0.15. Okay? My other answer wait a minute. Clear. 82.875 minus 6.37 divided by 2, divided by 255. 2.875. Let's see, let me check this again, because that's not looking good. So 82.875, clear, 82.875 times 82.875 equals 4 times 255 times 6.6937. Okay. Okay, come on. 82.875 minus 6.36 divided by 2 divided by 255. So I get one answer of 0.15. 82.875. Minus 6.36. Okay, something weird's going on here. Let me check my math because I'm doing it with my calculator, with my phone. And my phone doesn't work very well. All right, guys, I'm gonna write it all out. I'm gonna let you guys solve it because I'm using my phone and it's a bear. Well, no, hold on. Let's stop right there for a second.